Well, hello everyone. Welcome to this first chapter of our course, which is on temperature. So here is the summary of the main headlines that we're going to see in this chapter. So in the beginning, we are going to introduce the notion of thermodynamic variables or variables of state, which we use to describe a physical system from the macroscopic perspective. And then we are going to talk about the equilibrium states of a physical system. And once we know what these are, we can just formulate the zeroth law of thermodynamics. And from the zeroth law, we are going to be able to do two important things. On the one hand, we will be able to define a new variable of state or thermodynamic variable, which is temperature. It's the central variable in thermodynamics. And also from the zeroth law, we will have a means to measure that. In particular, we will discuss thermometry and how we measure temperature, and we're going to make an important distinction between the temperature that you can measure with a thermometer, which is what I would call empirical temperature, and the true thermodynamic temperature, which is the underlying thermodynamic property. So then we are going to introduce another definition, which is important. It's a distinction between adiabatic and diathermal boundaries in a system. And once we know what that is, we will be able to provide an operational definition of heat. So we are not going to explain what heat is at the moment. We're just going to give a means to measure heat exchanges based on temperature changes. Okay, so let's start with the content. And the way we will start is to think about any physical system you like. So, for instance, I don't know, a piece of solid, some dielectric material, or some, I don't know, whatever solid you like. And we know that this is going to be made of a large number of molecules, and molecules are made of atoms. And in the end, we can think of this classically. Okay? We can think of this system as a bunch of tiny particles that are somehow occupying certain positions in a certain lattice structure, and well, it's a large number of them, n. And if I want to specify what's the state of this system, well, in principle, I would need to tell you where are each one of the atoms making this piece of solid material, yes? And for that, well, I have to provide position vectors for each one of these guys. So I don't know, put coordinate origin here, and I have to supply, well, the x, y, and z coordinates of the position of each one of the single individual atoms there. But not only that, we know that since if we are going to have a classical description of this system, we know that we would be feeding the data that we know about the system into the equations of motion to solve the equations of motion and have all the information about the system as time evolves. And we know Newton's equation of motion are second order. So we don't only need the initial condition on the coordinates, we actually need an initial condition in the derivative with respect to time of the coordinates as well, so the velocity, something we need to supply. So velocities of these atoms that are in principle making small vibrations around their equilibrium positions. So the number of atoms or molecules that there could be in a macroscopic piece of material like this is of the order of 10 to the 24, like an Avogadro number. And this is a huge amount of information. So what I want to say with this is if I wanted to specify the state of a physical system really completely fully like this at the microscopic level, well, that would be a completely unworkable amount of information. And you know from experience, from what you have learned in electromagnetism, what you have learned in also mechanics, that when you deal with macroscopic systems, you don't work with nearly as many variables. For instance, in a case like this, well, you have a piece of material that has certain volume, and you can maybe apply some pressure on this object, that the pressure would be an important variable that you would use to describe the state of the system. And then, you know, if for instance this piece of material happens to be dielectric, well, then you would describe it by specifying what's the externally applied electric field, and then what's the the corresponding polarization that you can make in this material. Or imagine if the material is, for instance, magnetic material. So then you would, if you were to apply some external magnetic field with intensity H, well, you know the system will respond getting magnetized with certain magnetization M. And in general, these kind of variables are going to be the relevant variables that you use to describe this system. Yeah. So it's a handful of them. Of course, they are not anywhere close to the order of 10 to the 24. And the reason why you have few variables to describe a really complex system is because you are looking at the system from a macroscopic perspective. Or if you like, what you're doing is you are measuring the system with blunt instruments, which are macroscopic instruments, that instead of providing you detailed microscopic information about its microscopic state, are giving you coarse grain, time average, and spatial averages of this information. For instance, think of a camera. Imagine that you want to take a photo of this system as a means to measure it. Or if you like, imagine you want to make a microphotography of this system. Well, a typical shutter of a camera has a time in which it opens and closes, which is of the order of like 1/100 of a second. Okay, so this is the time that it takes for the image to be formed in the film of the camera. So the shutter lets the light through, and the light coming, being scattered by this object, is coming into the objective of your camera, and it's impinging on the chemicals in the film and creating the image. Well, this is the time scale that the measurement takes. Okay, and then the typical dynamical scale of molecular dynamics in a system like this is of the order of 1 femtosecond, 10 to the minus 14, I believe. Well, anyway, terribly small. So there is a huge difference between 10 to the minus 2 and 10 to the minus whatever. So there are really, really very many orders of magnitude. So actually, when you take a picture, it's not a still of the system frozen in time. It's actually a very long time average of the system doing all sorts of many different types of motion. Okay? So because you're making blunt measurements with blunt instruments, there is a lot of degrees of freedom that stop to be relevant from the macroscopic perspective, and that's the reason why you can get away with describing the state of your system with a handful of state variables, okay, or variable of state or thermodynamic variables, if you like. Okay.